So hello everyone, welcome you all to live session 5 of NPTEL course Fluid Flow Operations taught by Professor Shubhrata Kumar Majumdar. My name is Nagfan Sai Kumar. I am the teaching assistant for this course. So currently we are in week 5. Last week, that is on week 4, we discussed about the one-dimensional flow, and we also derived a couple of equations, basic equations which are mandatory for understanding fluid flow, which includes law of conservation of mass, conservation of energy, and conservation of momentum. Okay, so this week we'll be discussing about flow of viscous fluids. So we'll be basically deriving Navier-Stokes equation, and we'll also be looking at few cases where we can apply and use this Navier-Stokes equation. But before going into this Navier-Stokes equation derivation, we need to first understand what meaning of viscous flow, right? So basically, we need to have an understanding of what is viscous flow, right? So what is viscous flow? So in general, like all the equations that we have derived until now, which are derived in the earlier class, all the equations, basic equations, they are based on ideal fluid. Okay, so we assume ideal behavior of fluid, and then we have derived all the equations. Okay, so what is an ideal fluid? Ideal fluid is nothing but a non-viscous fluid. Okay, so we assume that liquid is having zero viscosity. So that is a non-viscous liquid, and which is a ideal fluid. Okay, so based on ideal properties, we have derived all these equations. But in general, this is an assumption. Okay, so there is nothing called ideal fluid, right? Okay, so using this ideal fluid assumption, we have derived and discussed the basic equations. That is all the equations based on mass, energy, and momentum. Okay, but in practice, we don't have anything as such called ideal fluid. Okay, so every liquid, all the liquids that are existing in nature, they have viscosity, but there is nothing like ideal fluid which is having zero viscosity. Okay, so the fluids having viscosity are known as practical liquids or real liquids. Okay, similar to ideal gas and real gas. So here we all the liquids which are having viscosity, they are called real fluids or practical fluids. So flow of real fluids is also known as practical flow or viscous flow because they are having viscosity, right? So they are called viscous flow. So due to this viscosity, the real fluids differ from the non-viscous ideal fluids, okay? Because in non-viscous fluids, we will be neglecting the term which is related to viscosity, right? Okay, but here viscous forces will also be acting, right? So that has to be taken care of. So that is why real fluids differ from non-ideal or real fluids differ from non-viscous fluids or real fluids. So it offers frictional or shearing resistance to the motion of the fluid, as I've told you. So viscous forces will be acting. So because of these viscous forces, there will be friction causing. Okay, between the layers of the fluids, there will be friction, and also between layer and with the surface of the plate or pipe. Okay, there will be friction forces. So a continuous supply of energy is required to overcome this shearing force. Okay, so if the fluid is supposed to overcome, then we have to obviously give some energy, right? So a continuous supply of energy has to be there every time. So we have three basic equations. So the first one is principle of conservation of mass flow. Okay, so this is also known as equation of continuity. And then we have principle of conservation of energy, also known as energy equation. And then we have principle of conservation of momentum. So these are the three basic equations that we have derived in the earlier class, right? So in all these three equations or all these three laws, we assume that the fluid is ideal, right? Okay, or non-viscous. But whereas in practical case or in real cases, we don't have anything called ideal fluid, right? So obviously we have to take into consideration of all the viscous forces, which will cause frictional losses, right? So here comes Navier-Stokes equation for viscous fluids. So this was obviously proposed by Navier, who's a French engineer and physicist. So for in order to derive this equation, so let's assume a elementary fluid, elementary rectangular fluid. Let's say this is X and Y. Okay, so this is in stream of flow. Okay, so currently we are in two-dimensional. We'll be dealing with two-dimensional flow. So we'll be having both velocity in y direction and also velocity in x direction, right? Okay, so let's resolve this into different forces. So first, let's check velocity. Okay, so if we draw velocity profile for this elemental fluid, so dimensions of this elemental fluid will be d, u, and sorry, dx and dy. Okay. So in y direction, so in x direction, velocity will be u, right? So after passing through this fluid element, there will be a loss of energy, right? Loss or gain of energy, right? So let's denote it as dou u by dou x. Okay, so the final velocity will be u plus dou u by dou x, that is change in velocity into dx. Okay, this will be change in velocity. And also here initial velocity will be in y direction v. Okay, and the final velocity after passing the fluid will be v plus dou v by dou y into dy, right? So similarly, let's balance forces for pressure and angular deformation as well. So coming to pressure, so again we'll take, so this is going to be length of the dimension of the fluid element in y direction, that is dy, and this is the dimension of fluid element in x direction, that is dx. Okay, so again pressure will be P at the entrance of this fluid element, and at the exit it will be P plus dou P by dou y into dy. Okay, this is nothing but change. So it can be either a negative value or a positive value because you're taking derivative, right? So we can either get a negative value or a positive value. So the overall quantity, that is P plus dou P by dou y into dy, can be either less than P or greater than P. Okay. So press doesn't always mean you're adding something. So it can also mean that you're adding a negative quantity. Okay. So coming to y direction again, we have P and the final pressure will be P plus dou P by dou x into dou dx, sorry. And coming to third force, it is angular deformation. So last time we also discussed about this, right? So angular deformation will also be there when a fluid element is in when the element is in or whenever a substance is in fluid flow. So it will also experience angular deformation as well, right? So let's say this is the initial position of this particle. So after deformation, it let's say this is the position of the particle. Okay. So this is going to be our y dimension, and this is going to be our x dimension, that is dx. Okay. So obviously there'll be either stress or strain, which is they can either be an elongation force or they can be a compression force, right? So let's say here we are having elongation force. So tau, let's say this is in this direction, and here this is in this direction, gamma 1, and so this direction, this will be tau plus dou tau by dou x into dx. Okay. Similarly, in y direction, it will be tau plus dou tau by dou y into dy. Right? This is nothing but change. Okay. So let's also consider this element, and we'll try to derive a relation between tensile stress and shearing stress. Okay. So let's say this is the position of the fluid element initially. Okay. And you're applying a stress in this direction, or we are elongating the fluid element in this direction, x direction. Okay. So if you're elongating it, what happens to the y direction? Force will be in this direction, right? Okay. So when you're elongating the fluid element in x direction, so there will always be a compression force which is acting in the y direction. Okay. So the final position of the element might be something like this, getting elongated in x direction and getting compressed in the y direction. Okay. So let's resolve this. Let's take this section. Okay. So let me first draw it. Okay. So if here the element is being displaced right to a certain distance. So element is getting displaced in y direction through a certain distance, right? So in y direction it is compression force. So here it is elongation in the x direction. Okay. So just try to observe both these diagrams and you'll be able to identify all the coordinates. Okay. So let's say here the fluid element is getting compressed through a certain distance. Okay. So let's say this is dou y, or let's say this is dou y, dou v by dou y. Okay. And in y direction, let's say this is dou u by dou x. So this dou u by dou x and dou v by dou y, they should be same. Like even though they're in opposite direction, they should be same. Okay, because you cannot change the quantity of mass, right? But when you're increasing in one direction, it should always be decreasing in the same amount in the other direction. Okay, so you're elongating in x direction, so it will be compressed in the y direction, but through a same distance or through a same sorry, through a same displacement. Okay. So let's say your the elongation force that you're applying. Let's say this is sigma x, and this is also sigma x, but in the opposite direction, right? So this will be minus sigma x, and here let's say this compression force is sigma y, and this is minus sigma y because this is positive and this should be in negative direction, right? And the forces experienced by the flow, side of the element, let's say this is tau. Okay, so these are elongation forces. Okay, and this is a shear. So these are tensile stresses, and this is a shearing stress. Tau is a shearing stress which will be experienced by the side of the fluid element. Okay, so we'll use this when we are solving the problems. Okay, so whenever one side is facing an issue, whenever there is elongation one side, there will be compression the other side. Okay, so let's calculate force equations. Okay, so forces will be acting in both x, y, and z directions, right? So let's say let's represent it as fx comma fy comma fz. Okay, so what is the meaning of force, like, or how do you represent force in mathematical terms using Newton's second law? F is equal to ma, right? Okay, so force is nothing but mass into acceleration. Okay, so let's write the same thing. So we have F is equal to ma, right? So mass can also be written as density into volume. Okay, and velocity as change in, sorry, acceleration as change in velocity with time, right? So let's do the same thing here. So force in x direction will be density into volume. Volume will be dx into dy into dz. This is mass, and into velocity, change in velocity rate du by dt. Okay, and Fy will be dou into rho into dx dy dz, that is mass into change in velocity in y direction with time, rate of change of velocity in y direction, and Fz will be rho into dx dy dz into dw by dt. Okay, so let's the velocity change at time dt can be expressed as the velocity change at time dt. So let's say this is equation 1. Okay, combining all these three, let's say this is 1, and du can be written as dou u by dou t into dt plus dou u by dou x into dx plus dou u by dou y into dy plus dou u by dou z into dz, right? So if you differentiate this with respect to dt, we'll be getting du by dt will be equal to dou u by dou t plus dou u by dou x into dx by dt. Okay, and we have dou u by dou y into dy by dt plus dou u by dou z into dz by dt, right? So dx by dt, dy by dt, and dz by dt, so these quantities will represent velocity of a fluid in x, y, z directions, right? So if you just write them down, it will become dou u by dou t plus u into dou u by dou x plus v into dou u by dou y plus W into dou Z by, sorry, dou U by dou Z. Okay. So similarly, we can write for dV and dW as well. Okay. So for dV by dt, we can write this as dou V by dou t plus U into dou V by dou x plus V into dou V by dou V by dou y plus W into dou V by dou z. And similarly for z direction, it will be dou W by dou t, which is equal to dou W by dou t plus U into dou W by dou x plus V into dou W by dou y plus W into dou W by dou z. Okay. So if you substitute these velocities, values of these velocities in equation 1, okay? So let's say this is equation 2, 3, and 4, okay? So substitute 2, 3, and 4, 2, 3, and 4 in equation 1, okay? So this will give us fx is equal to rho into dx, dy, and dz. This is mass, right, into velocity, that is du by dt. So this will become dou u by dou t plus u into dou u by dou x plus v into dou v by dou y plus w into dou w by dou z. And fy will become dou v by dou t plus v into dou u by, sorry, this is u, right? U into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z. Okay. And for z direction as well, it will become dou in rho into dx dy dz into dou w by dou t. Okay. Plus u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z. Okay. So let's call this as equation 5. So combinedly, let's call this as equation 5. So whenever a body is in water, whenever a fluid is in fluid element, the fluid element which is in water, or let's say in the fluid, so this will be experiencing three different type of forces, right? So it will be body force, it will be second one will be pressure force, and the third one will be viscous force. So the first one is body force, second one is pressure force, and then we have viscous force. Okay, so let's try to represent them. So body force, that is FB. So let's say this is represented by BX, BY, and BZ. Okay, so B stands for body force, and the pressure force, let's say this is FP, and this is denoted by PX, PY, and PZ. Is pressures in x y directions, and viscous forces are FS, that is SX, SY, and SZ. Okay, these are the components in the three different directions. So if you want to express Fx, that is force experienced by the body in x direction, so that will be combination of body force in x direction, pressure force in x direction, and viscous force in x direction, right? Okay. So we can say that Fx will be Bx plus Px plus Sx, right? And similarly, force experienced by the body in y direction will be By, Py, and Sy, right? Summation of Pb, Py, and Sy. And similarly, Fz will be Bz plus Pz plus Sz. Okay, so let's say this is equation 6 combinedly. Okay, so these are the three different forces that are experienced by the body. Okay, so what are these body forces? So which forces will constitute or which forces are commonly called as body forces? So body force, that is Fb, is represented by Bx, By, and Bz. Okay, so these forces act directly through the mass of the substance or element. So these forces include a gravitational force, centrifugal force, and electromagnetic force. Okay, so Bx will be basically the combination of all these three forces: gravitational, centrifugal, and electromagnetic, right? So we can write this as x rho dx dy and dz. That is, so let's say x, y, z, capital X, capital Y, capital Z are the components, axis components of these body forces. Okay, so this can be written as, if they represent the body forces experienced by the mass of fluid, then we can write Vx as Bx, By, Bz as follows. Okay, and then we have pressure forces, right? So this is represented as Fp, also Px, Py, and Pz. Okay, so let's consider the fluid element. Okay, so let's say the flow is in this direction, that is in x direction. Okay, so the force exerted experienced by this side will be pressure into area, right? P is equal to F by A. So F will be P into A, right? So the pressure exerted on this face will be P into area of this element, that is dy into dz. And on this direction, pressure exerted will be P plus dou P by dou x into dx into area of the element, that is dy into dz. Okay. So similarly, we'll be having y and z components as well. So let's write them down. So Px will be, that is force experienced in the x direction will be initial force minus final force. So initial force is P into dz into dy minus final force, that is P plus dou P by dou x into dx into dz dy. So this will give us minus dou p by dou x into dx dy dz. So similarly in py direction it will be p into dz into dx minus p plus dou p by dou y into dy into dx dz. So this will give us minus dou p by dou y into dx dy dz. And similarly in z direction it will be p into dx dy minus p plus dou p by dou z into dz into dx dy. So which will give us minus dou p by dou z into dx dy and dz. Okay. So we have dealt with body forces, pressure forces, and now we are left with viscous forces, right? So let's also viscous force. So this is denoted by Fs, that is Sx, Sy, and Sz. Okay. So force in x direction due to angle deformation, that is represented by Sx1. So we can write. Let's refer back to this diagram. So here, so from this we can write, and also whenever there is a stress, it will also be experiencing strain, right? Okay. So let's say the strain experienced by the small field element be gamma. Okay. So the corresponding stress can be expressed as tau is equal to tau xy plus tau xz. So this can be written as mu into dou gamma by dou t, which will be equal to mu into dou mu by dou y plus dou v by dou x. Okay. So along with this, we'll also have mu into dou u by dou z plus dou w by dou x, which is equation 9. So let's say this is combined equation 8 and this will be equation 9. So Sx1 will be dou tau xy by dou y plus dou tau xz by dou z into dz dx into dy. Okay, because this is basically stress, right? So we want to calculate force. So we are multiplying with area. So this will give us mu into dou square mu by dou y square plus dou square v by dou xy plus dou square u, sorry, this is u, not mu, dou square u by dou z square plus dou square w by dou x dou z, dou z dou x dou y. So this will be 0 because this is in z direction. This will be 0 for x1. So this will give us mu into dou square mu by dou square u by dou y square minus dou square u by dou x square plus dou square u by dou z square. Okay, into dx dy and dz. Okay, so here we have already established, right? I forgot to mention this, I guess. So dou u by dou x should be equal to minus dou v by dou y, right? So if you differentiate this with x, it will become dou square u by dou x square, which will be equal to minus dou v by dou x dou y, dou square u by dou x dou y. So we'll use the same relation to replace this quantity. Okay, so we'll be instead of dou square v by dou x dou y, we'll be getting This is dou x, dou y. Okay, we'll be writing minus dou square u by dou x square. Okay. So forces in x direction due to elongation transformation, that is Sx2. Okay. So let's consider the rhombus that we were considering earlier. Let me go back. Yeah. So let's consider this same element. Let's say this is EFGH, EFG, and H. Okay. So inscribed in a fluid element, that is ABCD. Okay, of unit thickness, which is shown in the figure. So so let the flow be from elongated flow from x direction, and in y direction let it be a contracted flow. Okay. So in x direction we have expansion flow or elongated flow, and then in y direction we have compression or contracted flow. So this deformation in x and y directions provide a simple angular deformation. Okay, because of opposite directions. So like they'll be in 90 degrees, right? So it will be providing a simple angular deformation. So which will cause the rotation of the face of rhombus. Okay, so there'll be a small change in the or shift in the face of rhombus. So now we'll be calculating the deformation per unit time. Okay, so from there, so we'll be calculating deformation per unit time, that is velocity of angular deformation. Deformation per unit time or velocity of angular deformation. So this is expressed as d gamma by dt. So we can write this as dou gamma by dou t will be equal to square root of uh, 2 into dou u by dou x by dou uh, root 2. So this will give us dou u by dou x. This will be equation 11. So therefore, shear stress acts on obviously four faces, right? So it will be acting on all the four faces. That is E, F, G, H. So tau will be mu into dou gamma by dou t. That will be equal to mu into dou u by dou x. Equation 12. So for equilibrium of forces on which are acting on EG, that is on this face, okay, due to tensile stress, that is sigma x, and the shear forces tau on EH and HG, we can write sigma x as 2 into is root 2 into tau cos 45 degrees. It will be 2 tau. So sigma x will be 2 mu into dou u by dou x, right? So now consider the fluid element having sides dx, dy, and dz. Dz is basically thickness. So it's tensile stress in x direction will be at a distance dx. It will be sigma x plus dx will be equal to sigma x plus dou sigma x by dou x into dx. Okay, let's say this is equation 15. Okay, so if you substitute or let's say the tensile stress in x direction acts on the face of the area that is dy and dz. So sx2 in xy direction will be S x2 will be minus sigma x into x. So sigma x in x direction into dz dy plus sigma x in x at x plus dx into dz dy. This will be equal to minus sigma x plus dou x by dou sigma x by dou x into dx into dz by dz into dy, which will be equal to dou sigma x by dou x into dz dy dx. Okay, so this will give us 2 into mu into dou square u by dou x square into dz dy and dx. So let's say this is equation 16. So from this you can write Sx as Sx1 plus Sx2. Okay. So this will give us mu into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square into volume, it is dx dy dz. Okay. And Sy will be Sy1 plus Sy2, which will be equal to mu into dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square into dx dy dz. Okay, and similarly Sz will be Sz1 plus Sz2, which will be equal to mu into dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square into dx dy and dz. So let's say this is equation 17. So this is a group. So all the three equations combined, we'll call it as equation 17. So now substitute 7, 8, this 7, 8 and 17 in equation 6 in this equation. So we will be getting rho into dou u by dou t plus u into dou u by dou t, so dou u by dou x plus v into dou u by dou v dou y plus w into dou u by dou z. This should be equal to rho x minus dou p by dou x, that is body force, pressure force plus angular deformation force into mu into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. Okay, and we also have rho into dou v by dou t plus u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z, which will be equal to rho into y minus dou p by dou y plus mu into dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. Okay, and in z direction it will be rho into dou w by dou t plus u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z. This should be equal to rho into z minus dou p by dou z plus mu into dou square w by dou x square plus dou square W by dou y square plus dou square W by dou z square. Okay. So this LHS term, this is called inertia term, inertia term, and this is the body force term, and this represents pressure term, and this represents viscous term. And these three equations commonly are called Navier-Stokes equations. Okay, so you will be using them in many cases for solving many problems on Navier-Stokes equations. So if you have any doubts in this, you can ask me. This is going to be an important concept, Navier-Stokes equation. So if you have any doubts, you can ask me. You can post them in the chat box or unmute yourself and ask me. Okay, so if you don't have any doubts, let's see the cylindrical coordinates as well. This is in Cartesian coordinate, right? This is in x, y, z. Let's also see Navier-Stokes equation in cylindrical coordinates. So in cylindrical coordinate system. So the continuity equation in cylindrical coordinate system for a constant density will be, first let's write continuity equation. So we have 1 by r into dou by dou r into r v r plus 1 by r into dou by dou theta into v theta plus dou by dou z into v z. This will be 0. Okay. So normal and shear stresses in cylindrical coordinates for a constant density system and viscosity can be written as normal and shear stresses in cylindrical coordinates for constant density and viscosity. So we can write this as sigma rr is equal to minus p plus 2 mu into dou vr by dou r. Then we have sigma theta theta will be equal to minus p plus 2 mu into 1 by r into dou v theta by dou theta plus vr by r. And this sigma z direction will be minus p plus 2 mu into 1 by z into dou v z by dou z plus vr by r. Okay. And similarly, shear stress will be tau r theta will be equal to mu into r into dou by dou r into v theta by r plus 1 by r into dou v r by dou theta. and we have tau theta. Tau will be equal to mu into v theta by r plus 1 by r into dou v z by dou theta. And then we have tau z theta will be equal to mu into dou v r by dou z plus dou v z by dou r. Okay, so this is for cylindrical coordinate system. So the Navier-Stokes equation in cylindrical coordinates for constant density and viscosity will be Navier-Stokes equations for constant density and viscosity. So this is in cylindrical coordinate system. Okay, so first component, that is R component. So R component will be rho into dou VR by dou T plus VR into dou VR by dou R plus V theta by R into dou VR by dou theta plus, sorry, minus V theta square by R plus Vz into dou Vz by, so dou VR by dou Z. Okay, this should be equal to body forces, that is rho g R minus dou P by dou R is pressure force, pressure term, plus viscous term, that is mu into dou by dou R into 1 by R into dou by dou R into R VR plus 1 by R square into dou square VR by dou theta square minus 2 by R square into dou VR by dou theta plus dou square VR by dou Z square. Okay. So cylindrical coordinates is a bit complicated, right? So that is why we are having these many terms and bit confusing. So don't worry. So if you are comfortable with cylindrical system, you'll be able to understand this. Okay. So then we have theta component. So this can be written as dou t plus dou v theta by dou r plus we have VR as well. Okay. Plus v theta by r into dou v theta by dou theta minus VR v theta by r plus Vz into dou v theta by dou z. So this should be equal to rho into g theta minus 1 by r into dou p by dou theta plus mu into dou by dou r into 1 by r into dou by dou r into v theta plus 1 by r square into dou square v theta by dou theta square minus 2 by r square into dou vr by dou theta plus dou square v naught v theta by dou z square. Okay, so and then we have z component. So this will become rho into dou v z by dou theta plus dou t plus vr into dou v z by dou r plus v theta by r into dou v z by dou theta plus vz into dou vz by dou z. So this should be equal to rho into g z minus rho P by dou Z plus mu into 1 by R into dou by dou into R V Z by dou R plus 1 by R square into dou square V Z by dou theta square plus dou square Vz by dou Z square. Okay. So if we take an example, I think we'll be late. So I'll just move on to the next concept, that is velocity distribution of a laminar flow. Okay, so in the Navier-Stokes equation, the convective acceleration in initial terms is a non-linear term. Okay, so it will be difficult to obtain analytical solution for general. It will be difficult to obtain analytical solution for general flow. So the strict solutions obtained to date are only for special cases. So one is for flow between parallel flows. The other one is flow in circular pipes. Okay. The first one is flow between parallel pipes or parallel plates, sorry. And the other special case is flow in circular pipe. So these are the only two special cases where we got a strict solution or exact solution using Navier-Stokes equations. Okay, so but for other cases we will not be able to do it because the acceleration term is a the convective acceleration term is a non-linear term. Okay, so but before going solving this problem, so let's go back and revise few concepts. So we already discussed about laminar and turbulent flow, right? So how do we distinguish between laminar and turbulent flow? We will be using something called Reynolds number, also represented as Re. Okay. So if Re for a particular fluid stream, if Re is less than 2300, okay, we call it as a laminar flow. Okay. We call it as laminar flow, and this laminar flow is predictable, and there will be slow mixing. And if Re is in between 2300, let me write like this: 2300 Re less than 4000. So then this is called transitional flow. Transition flow. So here we have turbulent outbursts. So turbulence starts in this region, and then we have Re greater than 4000, which indicates that we are in turbulent motion. So this is unpredictable, and there will be rapid mixing. Okay, and how do we represent Reynolds number? Re is given as rho u by d, rho u d by mu. Okay, so also written as inertia force by viscous force. Okay, so this is a non-dimensional number. So for the first case, that first special case that we are discussing, that is flow between parallel fixed plates, flow between parallel plates. So even in this first type, so in flow between parallel plates, we have fixed plates And then we have moving plates. So we have two cases again in this. Okay. So there's a name for this as well. I'll write it down in a while. So flow between parallel fixed plates. So this is called Poiseuille's flow. Okay. This is Poiseuille's flow. Okay. So let's consider a flow of a viscous fluid between two parallel plates. So let me write down or let me draw the figure. So let's say this is a fixed plate and this is also a fixed plate and they are parallel to each other. And let's say a fluid, viscous fluid is flowing in the stream. Viscous fluid is flowing between the two parallel plates. So this has just passed the inlet of the flow and this is at laminar conditions. So this will be your U max and this is the velocity at any location U. Okay. So if the fluid is if the velocity is only U, then that is in only in di one dimension, then U V and W will be zero. If the flow is steady, then U does not change with time, right? If flow is steady, U does not change with time. So dou U by dou T will be zero. Okay. And if there is no body force, we can write rho x as zero. That is a body term for body term which was in Navier-Stokes equation, right? So that will be zero. And if the flow is uniform, then U will also not change with position. If the flow is uniform, U does not change with position. So dou U by dou X will also be zero. Okay, so these are the assumptions or conditions that we'll be taking for this case. So if you apply or if you consider all these cases and apply them in Navier-Stokes equation, we'll be getting. First, let's write down the Navier-Stokes equation. So that will be rho into dou U by dou T plus U into dou U by dou X plus V into dou U by dou Y plus W into dou U by dou Z, which will be equal to rho X minus rho P by dou X plus mu into dou square U by dou X square plus dou square U by dou Y square plus dou square U by dou Z square. Okay. And we also have dou square V by dou T plus U into dou square V by dou X plus dou square V into dou square V by dou Z, sorry, dou Y plus W into dou V by dou Z is equal to rho into Y minus dou P by dou Y plus mu into dou square V by dou X square plus dou square V by dou Y square plus dou square V by dou Z square. Okay, and in the Z direction it will be rho into dou W by dou T plus U into dou W by dou X plus V into dou W by dou Y plus W into dou W by dou Z, which will be equal to rho into Z minus dou P by dou Z plus mu into dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square. Okay, so we know that you will not change with time. Also, you will not change with position, right? So these terms will also be zero. And we know there is no body force, so this will be zero, this will be zero, and this will be zero. Okay, and in YZ directions, there is no flow, right? So this will be zero, this will be zero, this will be zero. So all these quantities will be zero. There will be no pressure difference as well, and these terms will also be zero. Okay, and dou square u by dou x will also be zero, and dou square u by dou z will also be zero. So u is changing only with y direction, right? So this will be the only term which is left. So we'll be left with mu into dou square u by dou y square will be equal to dou p by dou x. So let's say this is equation 1. Okay. So you can either use this or maybe you can do this in a different way. So let's consider the fluid element. So let's take again two plates, two parallel plates, and let's say let's consider a fluid element here, which is having dx and dy as dimensions, dx and dy as dimensions. So this is the pressure force, and the viscosity or shear stress will be dou t plus dou t by dou y into dou dy, and this will be p plus dp by dx into dx. Okay. So now balance all the forces. Consider balancing all the forces. Then again, you will be, if you do it right, you will be getting the same term. Okay. So as there is no change in momentum between two phases, we can write the equation as p into dy minus p plus dp by dx into dx into dy minus tau dx plus tau plus the d tau by dy into dy into dx will be 0. That is equation 2. So just cancel out all the terms, all the similar terms. Okay. So this gets cancelled out, and you will be left with d tau by dy will be equal to dp by dx. Okay. So since we have tau as mu into d u by dx, if you substitute this in this equation, we'll be getting we'll be getting mu into d square u by d square u by d y square, that is equal to dp by dx. Okay, that's his equation 3. So you got the same equation, right? Even if you do it from the equation of continuity or if you balance out the forces, you should be getting the same equation. Okay, so now let's take this equation 3 and integrate it. So what was the equation? Mu into d square u by d x square, which is equal to dou p by dou x, right? So let's carry out integration. Okay, we'll be getting mu into d u by dy. Oh, sorry, this is dy. Okay, this should be equal to dou p by dou x into y plus c1. That's his constant, equation 4. And if you further integrate this, you'll be getting u is equal to 1 by 2 mu into dou p by dou x into y square plus c1y plus c2. Let's say this is the second constant. Okay, so we can use boundary conditions and you will be able to solve for C1 and C2. So at bound, if you want to use boundary conditions, you can use this at y is equal to 0, okay, and at y is equal to h. So we have two conditions at y is equal to 0 and y is equal to h. U will be 0, right? So we'll use those conditions. Boundary conditions at y is equal to 0, u is equal to 0, and at y is equal to h, u will be 0 again. Okay. So if you apply both these boundary conditions, you have two conditions and you know you have two unknowns. You will be able to solve it. And if you solve it, so final equation will be u is equal to minus 1 by 2 mu into dp by dx into h minus y into y. And this equation is going to be a parabolic equation. Okay. This is a parabolic equation. Okay. So you can also calculate flow rate and also mean velocity using this. So let's see how we'll be able to do it. So at y is equal to h by 2, du by dx, du by dy should be 0 because at center point u is maximum, right? U becomes u max, right? So if it's a maximum, then its differential should be 0. At minima and maxima, du by dt should be 0. Du by dy should be 0, right? So if you use this condition, you will be able to solve for u max. So u max will be minus 1 by 8 mu. Sorry, if you substitute y is equal to h by 2 in this equation, you will be able to obtain u max, that is 1 minus 1 by 8 mu into dp by dx into h square. Okay, this is equation 7. So this is equation 6 and this will be 7. Okay. So now volumetric flow rate. How do you calculate it? So volumetric flow rate Q will be equal to area into velocity, right? So that will be integral 0 to h u into dy. Okay. Minus 1 by 12 mu into dp by dx into h cube. So just solve the entire thing, you'll be getting this. So that is equation 8. And mean velocity or average velocity will be u mean will be equal to q by h, that will be equal to minus 1 by 12 mu into dp by dx dp by dx into h square. Okay. So will you be able to modify this further? Like, can you write this in terms of u max? So just you can do one thing. You can just divide u max, u mean velocity and u max. Okay. So if you divide them, u mean by u max will be equal to minus 1 by 12 mu into dp by dx into h square. Okay. And this will be reciprocal, right? 1 by what is u max minus 1 by 8 mu into dp by dx into h square. So dp by dx and h square gets cancelled out. Mu also gets cancelled out, and you'll be left with 8 by 12. So u mean will be equal to 8 by 12 of u max, right? So this will be nothing but u mean, sorry, u max by 1.5. Let's say this is equation 9. Okay. U min is equal to U max by 1.5. Okay, so let's say this is equation 9. And now, what would be the shear stress? What will be the shear stress due to viscosity in this region? So that will be, what is the formula for shear stress? That will be tau is equal to mu into du by dy, right? Du by dy. So we already have du by dy, right? So just take this mu to the other side and we'll be able to get equation for du by dy. So if you substitute this here, or maybe you can directly use this equation. Okay. We also know value for C1. So using these boundary conditions, we already got value for C1. So you substitute it, and if you substitute this equation 4 here, you'll be able to get equation for tau, that is shear stress. So this will be equal to minus 1 by 2 into dp by dx into h minus 2y. Let's say this is equation 10. Okay. So now let's say L is the length of the plate, that is the entire plate in the flow direction. Okay. So let's say this is the length of the plate, that is L. And let's say dp is the pressure difference across these two ends. Okay. And if you integrate this in x direction, then we'll be obtaining minus dp by dx as delta p by L. Okay. So if you use this equation, or if you substitute this in equation 10, we'll be getting tau is equal to 1 by 2 into del p by L into h minus 2 by. And similarly, q will be equal to 1 by 12 mu into del p by L into h cube. Okay. So I just substituted dp by dx value as del p by del p by L. Okay. So if you use this relation, we'll be able to solve for this. Okay. So this is flow between parallel plates when they are stationary. Okay. So they are called Poiseuille's flow. So that condition is called Poiseuille flow. And coming to the next case, that is flow between parallel pipes when upper plate is moving. So this is called Cauchy flow. Okay. Flow between parallel plates where upper plate is moving. This is called Cauchy flow. Okay. Let me draw the diagram once. So this is stationary. The lower plate is stationary, and the upper plate is moving with the velocity u. Okay, capital U. And let's say this is resistance H, and the flow of profile will be something like this. So as the upper plate is moving, so the layer which is adjacent to this wall, it will try to attain the same velocity. But as this plate is stationary, it will be zero. Okay. So in this case, where upper plate is moving in x direction with a constant velocity, u or minus u depending upon the direction. Okay, u or minus u. So from boundary conditions, you can say u will be 0 at y is equal to 0, but u will be equal to capital U at y is equal to h, because as the wall is moving, the adjacent layer will also be moving with the same velocity. So it will be having same velocity result of the wall. So we'll be using the same equation. So here, instead of using these boundary conditions, we'll just change the boundary conditions. So if you change the boundary conditions as to this and substitute them in equation 5, we'll be getting u as 1 by 2 into del p by mu l into h minus y into y plus or minus u y by h. Okay. So plus or minus it depends upon the flow of the, sorry, depends upon the direction of the plate in which it is moving. So let's say if the flow of the fluid is in this direction and if this fluid is moving in this direction, so you'll be having plus direction. Sorry, we'll be having plus. But if the plate is moving in the opposite direction to that of the flow, we'll be having minus sign. Okay. So let's say this is equation 14. Yeah, 14. So now volumetric flow. Volumetric flow rate Q can be calculated as integral 0 to h u into dy, which will be equal to 1 by 12 mu into del p by L into h cube plus or minus u h by 2. So this will be equation 15. Okay. So again, we can also calculate maximum velocity as well in this case. So maximum velocity and its position depend upon the velocity of the plate, right? So if this is moving with a faster velocity, the plate is moving at a faster velocity, then it will be towards the wall. But if this is moving with a relatively slow velocity, it will be away from the wall. Okay. Maximum velocity and its position depends on the plate velocity, right? So at y is equal to y max, du by dy should be 0 because at that place we assume that you will be u max or u max star. Okay. So just differentiate and substitute the conditions. So y max will be, if you solve it, y max should be 1 by 2 into plus or minus u by h by del p by 2 mu l plus h. This will be the position of the maximum velocity. Okay. And u max will be del p by 2 mu l into a plus b into a minus b plus u by h. Okay. So here a is 1 by 2 into h and b is u by h by del p by mu l. Okay. So this is the case for plate in the direction of flow. If the plate is moving in the direction of flow, and u max will be del p by 2 mu l into a minus b, a plus b minus u by h. Just for the sake of simplicity, we are denoting as a and b. Okay, if you want, you can directly substitute these terms. Just for the sake of simplicity, I'm writing these two terms as a and b. And this will be the case if moving opposite to fluid flow. Okay, so these are the conditions. And so as we discussed, we have two cases, right? So one is flow between parallel pipes, parallel plates, and then we have flow in circular pipes. We have flow in circular pipe. So here we will be using symmetry because as is a circular pipe, we can use symmetry. So these are the adjacent walls, and this is the center of the pipe. So velocity of profile will be something like this, where this is U max, this is Y, and this is R in the direction of R, and this is X. Okay, and also if you draw a profile for shear stress, at the center it will be minimum, and at the edges it will be maximum. Okay, this is tau profile for shear stress. So consider flow in a long cylindrical pipe or circular pipe, which is an example of parallel flow of axial symmetry. So in this case, it will be convenient to use Stokes equation, okay? So which is basically in cylindrical coordinates. So we'll apply this here using the same conditions that we used before. That is, we only have velocity is only u. So that means Vt and V theta will be zero. Flow is steady. That means u does not change with time, right? So dou u by dou t will be zero. Okay, and there are no body forces, so this will be zero, and flow is uniform. So dou u by dou x will be zero. Okay, so if you use these conditions and substitute them in Navier-Stokes equation of cylindrical coordinates and simplify them, also use these boundary conditions. Okay, use the boundary conditions as well. So finally, you'll be getting, let me write down the boundary conditions as well. At r is equal to 0, so if you use r is equal to 0, you'll be getting infinite term, but as the term should be finite, C1 will become 0, and at r is equal to r naught, that is at surface, u will be 0. Okay, so this is dou u by dou y should be 0 because u is maximum. Okay, so if you apply this condition, uh, you'll be getting an infinite term, but as the term should be infinite, from this you can write C1 as 0. Okay, and from this you'll be able to find C2. So if you solve for the terms and substitute the boundary conditions, then you should be getting this equation, that is u is equal to minus 1 by 4 mu into dp by dx into r naught square minus r square. Okay, that's this is equation 24. This will be 20, right? This will be equation 20. Okay. So again, similarly, you can also find u max from this. Okay. U max will be minus 1 by 4 mu into dp by dx into r naught square. Okay. So this is equation 21. and Q will be equal to, that is volumetric fluid will be equal to integral 0 to R naught 2 pi 2 pi U into dr. So this will be equal to minus pi by R naught square, sorry, R naught power 4 by 8 mu into dp by dx. This will be equation 22. And U mean will be equal to Q by pi R naught square, which will be equal to minus R naught square by 8 mu into dp by dx, which will be equal to 1 by 2 into U max. This is equation 23. Okay. So you'll also be able to find shear stress as well from these equations. Okay, so I'm not going into that. You just have to substitute them. Okay. So again, if you say that dl is a pressure drop across the length L, then the pressure drop equation can be written as del P equal to 8 mu L into Q by pi R naught power 4. Okay, so this can also be written as 128 mu L by Q by pi D power 4. Okay, just changing into diameter, radius to diameter. So this will be equal to 32 mu L into U mean, okay, by D square. So this is called Huygens-Poiseuille's equation. Del P by L is equal to 32 mu into U mean by D square. This is the case for cylindrical coordinates. So just took this equation and then calculated dP by L. Is called Huygens-Poiseuille equation. So using this equation, you can calculate viscosity of a liquid by measuring the pressure drop across the pipe, circular pipe length. Okay. So there are a few more concepts that is characteristic of turbulent flow. Okay, and until now we are only dealing with laminar flow, right? We have to do the same thing for turbulent flow. Okay, so few things will be changing. Okay, velocity and all these terms will be changing, but we are running out of time. So if you have any doubts in that particular concept, like calculating in case of turbulent flow, if you have any doubts, you can ask me. Okay, sir has already taught this in the class, right? So if you have any doubts in that class, which was discussed by professor, you can ask me, or we can move on to the problem session. Sir also discussed about boundary layer theory, and if you have any doubts in these concepts, you can unmute yourself and ask me, or maybe post them in the chat box as well. I'll try to answer them. Also, if you want to increase, or sorry, if you want to reduce the resistance, like when two plates are moving, you'll be using lubrication, right? Okay, so has also discussed about the lubrication part. So if you have any doubts in these sections, you can unmute yourself or post them in chat box. I'll try to answer them. But if not, we'll move on to the problem session. What would be the properties of a good lubricating fluid? Classification of lubrication theories. Okay, so has discussed many concepts. So if you have any doubts in them, you can unmute yourself and ask me. But if not, I'll move on to the problem session. Any doubts? Okay, so if you don't have any doubts, then we can move on to the problem session. So coming to the first question, an ideal fluid is defined as a fluid which is compressible, option A, compressible, incompressible, option B, option C, incompressible and non-viscous, D has negligible surface tension. So what will be the characteristics of ideal fluid? It should be incompressible and it should also be non-viscous, right? It should be having zero viscous. So basically non-viscous. So that would be option C. Okay. Coming to second question, the fluid forces considered in Navier-Stokes equations are. So in Navier-Stokes equation, what was the equation? So rho into we have velocity terms that will be equal to rho x plus dp by dx plus mu into some viscosity terms. Okay. So this basically considered body forces, pressure forces, and also viscous forces, right? Along with that, we also have inertia terms as well. Okay, initial forces as well. Okay, so it will consider body forces, pressure forces, and also viscous forces. So that will be option B. Okay. So coming to third question, Navier-Stokes equation describes the motion of option A solid substance, non-viscous fluids. Option B, option C viscous fluids. Option D gas. So in Navier-Stokes equation, we are also considering viscosity, right, or viscous terms as well. So if you are talking about viscous terms, then it should be a non-ideal or real fluid. Okay. So if it's a real fluid, then it should be having viscosity, right? So it will be a viscous fluid. Option C. Okay. So in Navier-Stokes equation, the convective acceleration is in the initial term is option A linear, non-linear, C option C negligible, D none. So which of these following is correct? It is a non-linear term, right? So coming to fifth question, a low value of Reynolds number means that dash are large in comparison with dash. So what is Reynolds number? Reynolds number is, what is the formula? D U rho by mu, right? Okay. So this is also written as inertia force by viscous force. Okay. So if Re is low, then that means numerator is having a lower value and denominator is having a higher value, right? Okay. So that means viscous forces are large in number or having is higher in quantity and initial forces are lower. Okay. So if you compare them, so that would be option C. Okay. So coming to sixth question, consider a fluid which is flowing in between two stationary parallel plates. The velocity near the plate will be will be equal to. So whenever not only between two parallel plates, so even if there is a single plate and if the fluid is flowing over this plate, so at this surface or near the surface of the plate, the velocity will always be zero. Okay, so if this is a laminar condition, but here if this is a laminar condition, even in this case, this is a laminar, it will be zero near the wall. Okay, so this will be option A. So coming to seventh question, for the laminar flow of a fluid in a circular pipe of radius r, the Hagen-Poiseuille equation predicts the volumetric flow rate to be proportional to. So this we already derived the equation, so it will be r power 4, option D. Coming to eighth question, in turbulent flow, the average velocity is dash of maximum velocity. So it will be between zero point 0.8 to 8.5. So we did not discuss this concept, but sir has already discussed this. So the answer will be option C, that is between zero point 0.8 and 8.85. So coming to ninth question, the turbulent eddy viscosity varies with. So this concept we also did not discuss, but sir has already discussed this. So option A is pressure, B temperature, C pH of the fluid, and D flow conditions. So it will be varying with flow conditions. That is option D. Coming to 10th question, mixing length depends on velocity gradient, distance from the wall, both A and B, none of the above. So that will be option C, none of the above. Okay. So if you have any doubts, until now you can ask me either in the lecture part on the discussion that we had, or maybe in the sums that we or in the problems that we discussed. So if you have any doubts, you can unmute yourself and ask me. If you don't have any doubts, we can end this session. You can either post them in the chat box or unmute yourself and ask me. Okay, so if you don't have any doubts, we'll end this session now. Okay. Thank you, everyone. Thank you for attending the session. We'll meet on next Tuesday. Thank you.